Hey everyone, and welcome. Today, we're jumping into something that's absolutely fundamental for distributed systems, the two-phase commit protocol, or 2PC for short. If you've ever wondered how multiple different computers can all agree to do something together, or not do it at all, without making a huge mess, well, this is the explanation for you. Let's get right into it. So here's our roadmap for today. We're going to start with the absolute basics of what two-phase commit is. Then we'll see it in action, step by step. After that, we'll get into its secret weapon for surviving crashes, which is logging. And finally, we'll dive into the really interesting part, what happens when things inevitably go wrong, and how the whole system puts itself back together. All right, let's set the stage a little. Just imagine you're booking a trip online. You need the flight and the hotel. It's a package deal. You can't have one without the other, right? Well, that all-or-nothing guarantee, especially when the flight system and the hotel system are on completely different computers, that is exactly the problem two-phase commit was built to solve. At its core, 2PC is really just an agreement protocol. And, the name gives it away. It all happens in two main phases. Phase 1 is kind of like the voting phase, where every system gets asked, hey, are you ready to make this change permanent? Then, once everyone's voted, Phase 2 is the final decision, the commit phase, where the final call to either go ahead or just roll everything back is sent out to everybody involved. Now, to make this whole dance work, we have two key players. First up is the coordinator. You can think of the coordinator as the manager of the whole operation. It kicks off the request and is the one that makes the final decision. And then you have the participants. These are all the other systems, could be databases, microservices, whatever, that actually have to do a piece of the work. Okay, so this whole thing hangs on one simple but really powerful rule. For the transaction to actually succeed, it needs unanimous consent. Every single participant has to vote yes, I'm ready. If and only if the coordinator gets a yes from everyone, it will give the final commit command. But, and this is so important, if even one participant says no, or maybe it just doesn't respond in time, the entire transaction gets aborted. For everyone. It's all or nothing, no middle ground. All right, so theory is great, but let's actually see what this looks like in practice. We're going to visualize the actual flow of messages back and forth between the coordinator and all the participants, assuming everything goes right. So this diagram here, it lays out the two phases beautifully. Over on the left, you've got Phase 1. The coordinator sends out a ready or can you commit message to every single participant. They look at the request, and in this happy path scenario, they each send back a yes vote. As soon as the coordinator has all those yes votes in hand, we flip over to Phase 2 on the right. And that's when it broadcasts the final commit command to everybody. It's a really simple but effective call and response. Okay, so let's just formalize that flow, step by step. It all kicks off when a client sends a request to the coordinator. The coordinator then starts Phase 1, asking all the participants to vote. Once all the votes are in, the coordinator makes its big decision based on that global commit rule we just talked about. Then, it sends that decision out. And finally, the participants just send back a quick acknowledgement saying, yep, got it, it's done. Now, this all works perfectly in a perfect world. But, we don't live in a perfect world. What happens if a server just decides to crash right in the middle of all this? And this brings us to the protocol's real secret weapon, its memory, which takes the form of these super durable logs. Right? That's the big question. I mean, if the coordinator tells everyone to commit and then immediately crashes before it gets the final okay from everyone, how does it know the transaction was finished when it reboots? Or what if a participant crashes right after voting yes, but before it gets the final order? Let's see how logging solves this whole mess. So here's how it works. Before any system takes a critical action, it writes down what it's about to do in a permanent, durable log. Think of it like writing something down in permanent ink that's going to survive even if the power goes out. So for instance, a participant will write down its yes vote before it actually sends it to the coordinator. Then the coordinator writes down its final commit decision before it broadcasts it. And this whole idea, this write-ahead logging, is what saves the day. If a system crashes and reboots, it can just look at its log to figure out exactly where it was. That log becomes its single source of truth. All right, so now that we've got the whole logging thing down, we can get into the really tough part, failure. Let's actually map out all the different moments where something could break down and see exactly how the protocol is designed to handle each and every one. See, a failure can happen pretty much anywhere in this whole dance. To really get how 2PC handles this, we're going to break it down and look at several of these distinct failure scenarios, the ones highlighted right here on this diagram, to see how the protocol keeps things consistent no matter what. Okay, let's start with the easy ones. At point 1, the coordinator fails before it even has a chance to send out the vote requests. In that case, the transaction never really even got off the ground, so it's safely considered aborted. Then at point 2, maybe a participant fails before it can vote. The coordinator is just going to time out waiting for that vote, and since it didn't get a yes from everyone, it has to abort the transaction. Okay, now for point 3. This one's a really critical moment. The coordinator has gotten all the votes back, but it crashes before it can write its final decision down in its log. So when that coordinator eventually recovers, it has no record of deciding to commit. The only safe option here is to assume the whole thing failed and tell everyone to abort. Okay, so far so good. Any failure before the big decision gets made, we get a nice clean abort. But things get a lot more interesting now. What happens when a failure occurs after a decision has already been logged? Let's see how the system uses those logs to recover. So at point 4, a participant crashes after it's already voted and logged its vote. When it comes back online, it checks its log. If it logged a vote to abort, easy, it can just abort on its own. But if it logged a yes vote, it's suddenly in this weird limbo state. It's uncertain. It can't just decide to abort because for all it knows, the transaction was committed everywhere else. So it has to wait, and it has to keep asking the coordinator for the final decision until it gets an answer. Now, failure 5 isn't really a crash. It's just a lost message. What if the coordinator's final decision never makes it to a participant? Well, the protocol handles this with timeouts. The coordinator will just keep retrying to send the decision. And on the flip side, if a participant is just sitting there waiting for too long after it's voted, it can actually reach out and proactively ask the coordinator, hey, what was the final word? So this slide really shows the 2 paths a coordinator can take when it restarts. On the left, if the coordinator crashes before it logged a final decision, it's got no choice when it reboots but to abort the transaction, just to be safe. But over on the right, if it had already logged its decision to commit, that log entry is now its source of truth. It'll use that to get back to work, resending that commit message to anyone who might have missed it. So let's just boil all of that down into a simple playbook. Failures that happen before a decision is logged, that's points 1, 2, and 3. They always result in an abort. For failure 4, the participant has to check its own log. For lost messages at point 5, we rely on timeouts and retries. And for coordinator restarts, well, everything just depends on whether a final decision was saved to its log before the crash. And this brings us to the single biggest weakness of the two-phase commit protocol. What happens if the coordinator logs a commit decision, tells half the participants, and then just dies permanently? The other participants, the ones still waiting for that final decision, are now completely stuck. They can't abort because other systems might have already committed the change, but they can't commit either because they never got the official order. They are blocked. You know that feeling when a payment is just processing forever? This is basically why that can happen. This is the Achilles heel of two-phase commit. And that really is the final crucial question here. Two-phase commit gives you an incredibly powerful guarantee of consistency, but as we've just seen, that guarantee can come at the cost of availability, creating this very real risk of a system getting completely blocked. And this exact trade-off is what drove the development of even more complex, non-blocking protocols like Paxos and Raft. It's just one of the fundamental challenges in distributed systems. Thanks for joining me for this explainer.